Hi there, welcome to part 3 of the section on parabolas. Just a quick recap of what we learned so far. We learned that a parabola is the graph of any function of the form y of x equals ax squared plus bx plus c, where a, b, and c are fixed numbers, fixed real numbers, and a does not equal 0. So the parabola is the graph of any function of that form. In part 2, we also learned that for functions of the form y of x equals kx squared, where k, of course, still does not equal 0. It's exactly the same situation as before, except a equals k, b equals 0, and c equals 0. Well, we learned that in this situation, our parabola, our graph of these functions, looks something like this. So if this is x, this is y. Our graphs look something like that. And also, if we make k bigger, that stretches the graph out like that, because the y values increase faster for a bigger k. That should go through 0, 0. The y values increase faster for a bigger k. And similarly, if we make k smaller, it stretches the graph out this way, because for smaller values of k, the y values are all going to be smaller, so they're going to be less, and so that has the effect of flattening out the curve. And also, hope I've drawn enough room for this, if k is negative, it has the effect of flipping the whole thing upside down, because the y values are the same as what they were before, except negative, in the negative direction. So it's pretty much the same graph except flipped upside down, because we got negative y values instead of positive ones. Alright, so that's a quick summary of what we learned so far. In this section, what we're going to do is we're going to learn how to shift these graphs across in either the left or right directions. We're going to take a look at how that works. So, easiest way to explain these kinds of things is with an example. So let's do exactly that. This is the x-axis, as always. This is the y-axis. And this is our function. Let's draw it properly. Should be symmetric on both sides. This is the graph of the function y of x equals kx squared. And clearly k is positive in this picture I've drawn. But all the theory will still apply for negative values of k. Let's go ahead and plot a few points. So this is clearly 0, 0. We know our parabola goes through the point 0, 0, because when I put x equals 0 into this function, I get y of 0 equals k times 0 squared, which is equal to k times 0, which is equal to 0. So 0 is the thing that comes out of the function when I put x equals 0 into the function, and hence it is represented by our curve going through the point 0, 0. Okay, when x is equal to 1, what do we get out of this thing? Well, y of 1 is equal to k times 1 squared, which equals k times 1, which equals k. So k is the thing that comes out of our function when we put x equals 1 into it. Similarly, when we put x equals negative 1 into the function, we get k out. So it's symmetric on both sides. When x equals 2, what is it that comes out? When x equals 2, we get y of 2 equals k times 2 squared, which is equal to k times 4, so 4k is what comes out of our parabola. So, yeah, that's what happens when you put negative 2 into the function for the same reason. And finally, we'll plot x equals 3. When x equals 3, we get y of 3 equals k times 3 squared, which is equal to k times 9, so 9k. And similarly on the negative side, when x equals negative 3, because negative 3 squared is the same as positive 3 squared. Negative 3 times negative 3 equals 3 times 3 equals 9. So that's where we're at so far. Now what I want to do is I want to shift this entire thing across by, I don't know, let's say 3. I want to shift it to the right by 3. I want to move my whole parabola, wrong color. I want to move my entire parabola across by 3 units to the right. That's what I want to do here. And so, since I want to move my entire parabola across by 3 units to the right, we observe that when x is equal to 3, we should get 0 out of the function. Because I want to shift this curve across. Well, I've shifted that point there across by 3. So I should get 0 out of the function when I put x equals 3 into my function. And that gives us a hint of what our new function should look like. I'm just going to write it down, and we'll check that it works later. Well, to make sure things don't get confusing, I'm going to call this function here y1 of x, and I'm going to call my new function y2 of x. And y2 of x is going to be equal to k times x minus 3 squared. K times x minus 3 squared. And you will observe that, and I'm going to write over here because I'm running out of room, y2 of x is actually equal to y1 of x minus 3. So y2 of x, if I put x into the function y2, I get k times x minus 3 squared. And if I put x minus 3 into the function y1, if I put x minus 3 into the function y1, it would be the same, but with the thing in the yellow circle as x minus 3. So it would be y1 of x minus 3 equals k times x minus 3 squared. So y2 of x is actually equal to y1 of x minus 3. Put a wall there to make sure those y's don't get confusing. Well, what we're actually saying to the function there is basically, if I want to get the same thing, so if I want y2 of x to be the same as, to have the same value as y1, I need to push it 3 units across to the right. I need to push it 3 units across to the right. The reason for that is, well, again, we can take another close look at this function here. If y2 of x equals y1 of x minus 3, then what we also have is that y2 of x plus 3 must be equal to y1 of x plus 3 minus 3, which is equal to y1 of x, which is exactly what I was saying there. If I want to get the same value for 3 units to the right in my y2 function as y1 of x, well, I need to do exactly what I just did. I need to subtract 3 from my x value before putting it into y1. And so that's where this equation really comes from. Let's double check that everything works the way it should. We've sort of already proved it algebraically if you want, but let's go ahead and do some more calculations. If I put x equals 4 into my new function y2 of x, if I put x equals 4 into that, I want to get k out, because I want it to be the same as my function y1 of x, but moved 3 units to the right. Do I get k out? Well, yes, I do, because y2 of 4 is equal to k times 4 minus 3 squared, and 4 minus 3 is 1. Remember, you do brackets first. Brackets first. So y2, really running out of room here. y2 of 4 is equal to k times 4 minus 3 squared, which is equal to k times 1 squared, which is equal to k, because 1 squared is just 1. So y2 of 4 does indeed equal k. We'll check out the point 2 next. So x equals 2. Well, if x equals 2, I also want this thing to equal k, because when x equals negative 1, y1 of x is equal to k. So y1 of negative 1 is equal to k. Well, 2 is 3 units to the right of negative 1. So I want it to have the same y value when I put it into my function y2. I want it to have the same, I want y2 of 2 to be equal to y1 of negative 1. That's what I want. And does it? Well, let's double check. y2 of 2 is equal to k times 2 minus 3 squared. Well, k times 2 minus 3 squared is the same as k times negative 1 squared. And again, well, because we do brackets first, and again, negative 1 squared is the same as 1 squared, so we get y2 of 2 equals k times negative 1 squared equals k. So indeed, our y2 parabola does go through this point that we want. And you can check for the rest of them. So when x is equal to 1, which I've sort of covered up there, when x is equal to 1, we do indeed get 4k out, because y2 of our function y2, because y2 of 1 is equal to k times 1 minus 3 squared, which is equal to k times negative 2 squared, which is equal to k times 4, which is 4k. So, hallelujah. We can plot the rest of the points. I'm not going to bother, mainly because I'm running out of room. And we will find that everything works out as we'd hoped. And our parabola, our y2 parabola, is the same as our y1 parabola, except shifted 3 units to the right everywhere. So subtracting 3, by subtracting 3 before doing anything to the function, what we've really said is that y2 of x plus 3 must equal y1 of x, because it takes 3 more units to the right before we get the same thing out of the y2 function as what we did out of the y1 function. So we just successfully shifted our parabola 3 units to the right by subtracting 3. And in fact, yes, I want to clear. And in fact, for any, let me go back to black. In fact, for any positive k, I guess I shouldn't use k. For any positive, I don't know, d, for any positive d, for any positive d, how should I word this? For any positive d, subtracting d from x shifts the function, the parabola, or in fact the graph of any function, but in particular here, shifts the parabola to the right by d units. Shifts the parabola to the right by d units, i.e. y2 of x equals k times x minus d squared is the same, on red, is the same parabola as y1 of x equals kx squared, but shifted right by d units. Okay, so that's a bit of theory. I know it looks a little bit like a child scribbled it with a crayon, but hey, the math is still sound, don't worry. I'm going to cut it right there for now, and we'll finish off this kind of moving the parabolas around in the next section. Thanks very much for watching. Take care. See you next time.